Hi, linear algebra students. We are in section 2.2, inverse of a matrix. Just following up on what we've done in class, I want to remind you that in this section, we're categorizing square matrices into two kinds, invertible or non-invertible. And depending on which category a square matrix belongs to, there's very, very specific consequences that fall from that. So this is what we're establishing, okay? We're establishing, first of all, how do we know if a matrix is invertible or not? And if we know that a matrix is invertible or not, what are the consequences of that? Okay? And in this video and the two next ones, I'm going to explain a little bit, we're going to prove one of the most important theorem in this section pertaining to elementary matrices, to be more precise. Okay? So let's read this theorem, and then I'll explain why it is so important. If an elementary row operations, row is a very big keyword here. So if an elementary row operation is performed on an m by n matrix A, okay, the resulting matrix can be written as a product, so as E times A, where E is a m by m, so number of rows, right? Elementary matrix obtained by performing the same row operation on the identity matrix. Okay? So again, I want to stress the word row here because proving this theorem requires a very good understanding on how matrix multiplication is affecting the rows of a matrix. Okay? And why is this theorem so important? It's because this is the theorem that allows you to prove that if a matrix row reduces to the identity matrix, remember we're talking about square matrices, then it's invertible, okay? And everything can snowball from there. All right, now why am I underlining the rows so much? It's because to prove this theorem, we need a very important fact about matrix multiplication. So let's write this down. To prove this, we rely on this theorem. Row I of AB is equal to row I of A multiplied by the matrix B. Okay? And what does this mean? Okay, this equation right here, let's just sketch dummy matrices. So what's happening is that if this is the height row, okay, right here, okay, and B, we just let's say sketch its columns like that, okay, then the height row of AB will depend only on the height row of A and not of the other rows, okay? That's the important fact. So here you go. So what I mean by this is really what I just said. So the height row of AB depends only on the height row of A, not of its other rows, right? Okay, so this is what we will use. All right, now I'm erasing this, and I will prove the first part. So with the first row operation, which is the permutation. And the next two, which is the scaling and the row replacement, we will prove them in the next two videos. So that's why I'm doing 3 videos on this theorem, 1 per elementary row operation. So let's go. So ERO number 1, which is row I permutation with row J with, okay, so here I'm going to explain my notation a little bit. What I'm describing here is that I'm permuting 2 rows, and the labels I and J can be anything between 1 and M. Okay, and they're both independent, right? They most of the times they're not the same. Actually, they need to be not the same, otherwise we're not doing anything. So actually, we could also write I is not equal to J. It's not that important, but just to be very, very specific, it's nice. And what we're gonna do is in the proof of each of the EROs, we're always gonna consider E to be the matrix obtained from IM with the same elementary row operation. So let's put it this way. Consider E to be the elementary matrix obtained from IM by the ERO Okay, so here's what we're going to do. K is not equal to I, K is not equal to J. Or actually, even better, I will write row K, where K is not equal to I, and K is not equal to J. Okay? So what we will do is we will prove that the kth row of EA and the kth row of A are the same. Okay, so that's the first thing we need to do. So what we do is this. We consider the row K of EA, and we use the equation that I put on the board a while ago. So that's going to be the row K of E multiplied by the matrix A. And now here's the central argument. Since that's it, K is not equal to I, K is not equal to J, so we're talking about a row that is not involved at all in the permutation. So it means that it turns out that it's the same as the row K of I, right? Because it's not one of the rows that has been changed at all. Multiplied by A. Okay? Then we use this operation again, but now on the reverse, right? So we say row K of IA, and it turns out to be row K of A. Okay. So what's important is this thing. Okay, so I'm actually going to underline this in red. And now I'm going to consider the case number 2. Let's say we're talking now about the row I. And I'm actually going to even erase the theorem. That's going to be very convenient for this problem. So case number 2. Row I. So now I'm talking about one of the 2 rows that have been permuted. Same exact procedure. So row I of E times A. This is the same as the row I of E multiplied by A. And now here's the key argument coming up again. Now, we know that we had IM and we obtained E By the elementary operation, row I permuted with row J. Okay? So in other words, the row I of E is the same as the row J of I. So here's the slight difference. All right, and then after that, we regroup as we did before. So this becomes the row J of IA, which is the row J of A. Okay? We have to do the same thing for the row J, and you will very soon see why. So case number 3. But keep in mind that for case number 3, it's actually the exact same procedure. So you have row J of EA, which is equal row J of E times A. And now the same argument comes in, right? Since the row J has been permuted with row I from the identity matrix, we know that this will be the row I of the identity matrix times A. And again, we have here row I of IA, which is row I of A. Perfect. Now we have seen all 3 cases, and I'm quite lucky that we have them all on the board. Okay? Now what we need to do is to summarize and conclude. Okay? So we have seen that for K not equal to I, K not equal to J, we have seen that row K of EA is equal row K of A. So in other words, the same rows at the same position. Now for row I, so let's say I will say here K is equal to I. We have that row I of EA is equal row J of A. And same thing when K is equal to J. We have that the row J of EA is equal the row I of A. Taking this all together, it means that EA can be obtained from A by simply permuting row I and row J. Because otherwise they have the same rows. It's only in this scenario that the rows are reverted. Okay, so that's how you can conclude. So E times A is obtained from A by the ERO and this is the end of the proof for, remember, the first ERO. Keep in mind where we started, right? We never assumed that this was true. This is really the important aspect of the proof. What we did is we are considering the permutation. We are getting the elementary matrix, knowing that we want to do a permutation. So that's what the E is, and we compare the rows of EA with the rows of A. And from this table right here, the conclusion is that EA and A are the same matrices, but with the row I and J interchanged. So that's how we can conclude that EA is obtained from A by doing that elementary row operation. I hope that helps your understanding. In the next video, we're doing the same thing, but with a scaling operation. See you there.